Hey everyone, my name is Paul Megan. I'm here with my friend Mallory Gershenfeld. We work on Amazon S3, and our job today is to take you through everything that the S3 team has built over the course of the last 12 months since we were all here together at reInvent last year. And we've been pretty busy, and so we have a lot of content to cover today. We're going to take you through 30 launches in the next 60 minutes. We've structured the talk into these 4 categories. We're going to talk about structured data and unstructured data, 2 big launches that were in Matt's keynote this morning. Then we're going to take you through what we're up to on the fundamentals, so scale, security, performance, durability, those things about S3 that we would prefer you not have to think about. And then we're going to wrap up the talk with an update on our client portfolio. So every year we set this session at the 200 level. We do that just because it's such a broad talk. But we don't have time to dive deep into every single launch today, but Mallory and I will stay after the session for as long as it takes to answer any questions that you have, because we want to make sure that you do have the details that you need to go home and put some of this stuff to work. So, with that said, we're going to get started with structured data. Now, traditionally, if you look back to the beginning of S3, the first workloads that we got were really unstructured data sets, things like images and videos, logs and backups. And these are still very important workloads for us, and there are huge unstructured data stores in S3 today. We talk about unstructured data all the time with customers. However, over the course of the last several years, you all have taken us in a completely different direction as well. And today, Amazon S3 is also a tabular data store. If you look at a single data type, Apache Parquet, we have exabytes of Parquet storage in S3 today. It's effectively become the de facto standard for storing rows and columns in S3. We serve more than 15 million requests per second off of that Parquet data, which equates to hundreds of petabytes of data transferred between S3 and compute every single day. So that's a lot of data, and it just indicates just how much work you're putting in on S3 with tabular data sets, mostly powering analytics applications. Now, over the last several years, you all have innovated on top of all of this Parquet data in S3 and established a concept called the open table formats. The most popular open table format today is called Apache Iceberg. And just as a quick primer for those of you who aren't super familiar with Iceberg, what it does is it defines tables in metadata files within S3. This means that the concept of the table, as well as the underlying data files, which live in Parquet, exist entirely within an S3 bucket. Then a query engine, like Amazon Athena, understands the Iceberg standard and can use the Iceberg metadata in order to translate a simple SQL query into S3 API calls to go and retrieve the necessary ranges of data within a bunch of underlying Parquet in order to fulfill the answer to that query. And what's cool about this architecture is that you have this sort of separation of concerns where the tables are defined and as tables as well as the underlying data files are all living within S3. And you can bring a range of query engines to bear against those tables. So you can query your tables in Athena, you can query those same tables in EMR, QuickSight, open source Spark, and on and on and on. This has been a very effective architecture for customers, this pattern of separating query engines from the underlying data and metadata associated with the table, and it's commonly referred to as a lakehouse architecture. This architecture has been deployed thousands of times over the course of the last several years. And as we've helped customers scale their lakehouses to petabytes and beyond, we've noticed a few themes in terms of problems that they face as they get deep into their data lake journey with Apache Iceberg. The first problem is that more scale requires more performance. This is especially true if you have a table, an Apache Iceberg table in S3, and you want to share it across multiple query engines within your environment. The second problem is that since tables are defined in metadata, it's not as straightforward as security is not as straightforward as assigning a bucket policy or a policy that protects a specific prefix. And the third problem is that optimizing storage cost underneath these tables requires a bit more work. You have to really understand which data can be expired, and normal, just off-the-shelf lifecycle policies just don't work. And this is why we're so happy to announce this morning in Matt's keynote the launch of Amazon S3 tables, which are fully managed Apache Iceberg tables within Amazon S3. S3 tables are delivered to you within a new bucket type that we call a table bucket. And what makes a table bucket different is that it has table-specific APIs that you can call in order to create and manage your tables. So you have basic CRUD operations for creating, listing, updating, deleting tables. You also have some control plane APIs for managing the underlying Apache metadata. So you can find the top level of the iceberg metadata, and you can easily commit transactions down to that metadata in a very safe and consistent way. Now, when you go create an iceberg table within a table bucket with our Create Table API, that table is a first-class AWS resource. It has an ARN, it has its own endpoint, and you can hang a policy off of it. And this is very significant architecturally, both for you and for us. When you bring in your query engines, like Athena or EMR, you point those query engines at one of these tables. And since we've elevated the level of abstraction up to the table level, we're able to automatically optimize the storage and the data path behind that table in a way that is very specific to Iceberg and Parquet. Since we know that all the data within that table bucket is in fact Parquet, is in fact Iceberg, we can take some shortcuts and we can make tables better on your behalf. And there are really three ways in which we can do that. The first is on performance. We're able to make tables just faster based on the way that we're able to lay out data across S3's namespace and optimize S3's index to deliver more TPS. The second is that we're able to simplify security for you. Since every table is a resource, you can now handle security controls for your Iceberg tables with the same way that you handle security for a bucket or a prefix or an access point. And we automatically cost optimize under the hood on your behalf. I'm going to take you through each one of these in a little bit more detail, starting with performance. S3 tables deliver up to 10x TPS improvement and up to a 3x improvement in query performance. Now, these are kind of big numbers, and whenever I show numbers like this in this session, I like to just take the engineers in the room through how we got to these numbers, okay? So I'm going to go through each one just so you understand the math behind the marketing here. On the 10x TPS improvement, we've come to reInvent for many years, and there are many examples of talks that we've given about improving S3 performance based on key naming. Key naming is a critical input to how we spread data out across our index, and it's a key input into driving more TPS from S3. Since we're able to optimize key names on your behalf when data passes through one of those table endpoints, we can name the underlying Parquet in such a way that it's spread out across S3's namespace in a very even and optimized way. Additionally, we tune the underlying index, which is our underlying metadata subsystem within S3, specifically for Iceberg and Parquet workloads, since we know that all data within a table bucket is Parquet, is Iceberg. Because of these two optimizations having to do basically with our S3's underlying index, we enable a higher starting point for TPS compared to a general purpose bucket. I included a link to a blog post that we posted out last week. It's a case study with Amazon Ads, and it dives deep into the relationship between S3 TPS and Iceberg. It talks about some open source contributions that we've made to Iceberg leading up to this launch. And so if you want to understand that relationship better between sort of Iceberg and S3 TPS, all the details, gory details, are in that blog post. I encourage you to take a look. Now, when we say that S3 tables are able to deliver up to a 3x improvement to performance, where that is coming from is through automatic data compaction behind the scenes. An iceberg table is backed by a number of Parquet files. When it's backed by a large number of small Parquet files, we have to make a lot of requests down to S3 in order to get the data that we need in order to fulfill a SQL query. This means there are lots of requests made, there are tail latencies become a problem, and this makes your queries slower. With S3 tables, we automatically compact the underlying data files on a regular basis, on a continual basis, in order to make sure that we're always compacting many small files down to a few large ones. We do this without you have to worry about it, and we do it by default. This means that fewer requests have to be made down to storage in order to fulfill your queries. It means that tail latencies are reduced, which have a big impact on the overall performance of a query, overall time that it takes to complete a query. And since each one of these gets from the underlying storage is larger, because it's coming from fewer, larger files, we can parallelize the payload coming back and increase throughput. That's how we get to this 3x number. That's what it means. The link at the bottom of this screen points to a benchmarking blog that we actually will post tomorrow. So if you look at it right now, you'll see a 404. But tomorrow you'll see a blog at that link that shows like the testing rig that we used in order to test against the TCP/DS benchmark in order to get to this 3x number. And so if you want to go take a look at the math behind this number, please do. It also gives a good overview on how compaction works and why to compact Parquet in order to make your queries go faster. So that's the story on performance. That's the math behind the marketing of an up to 10x and an up to 3x query performance improvement, these numbers that we're talking about here in association with this launch. Now, on the security side, since tables are resources, we now have the ability to go hang normal IAM resource policies off of those tables. This is super useful in situations where you want to enable permissions across many end users driving separate query engines to go access, read, and write to a shared set of tables. Customers have told us this many times, that that's what they want to do. They want to, in their lakehouse environment, establish sort of coarse table-level security controls across the data lake. And now that you can explicitly assign permissions to individual tables, you now have the ability to do that. Additionally, you can write bucket policies, just like you can with general purpose buckets, that establishes permissions out across of all your tables or to individual or subsets of tables within the bucket. This gives you the ability to just use the same security paradigm that you have with all of your AWS resources for your iceberg tables, which have traditionally been kind of squirreled away in metadata, okay? So that's how we simplify security with S3 tables, by just making tables first-class AWS resources. On storage cost optimization, we talked about compacting data down to fewer large Parquet files backing an iceberg table. This is great for performance. Over time, these tables will grow, more snapshots will be stored, there will be garbage associated with your tables, associated with deleted rows and stuff like that. And so your tables will grow and grow over time. And in order to delete data out from underneath your tables, you really have to understand how the underlying Parquet maps back to the Apache Iceberg metadata so you know what to delete. And to help customers do this, we do nightly maintenance runs within table buckets to do snapshot expiration as well as garbage collection. These processes run automatically behind the scenes without you having to physically manage them in any way. They're very similar to what you're used to with S3 lifecycle policies. Here's an example of one of these maintenance policies being set at the command line. You can see we're defining the number of snapshots to retain and the amount of time that you want to retain these snapshots. Very similar to what you would expect from lifecycle, just expiring normal S3 objects. Okay? So that is table buckets. It's a big step for S3. We're very excited to get this to you, and it's GA as of today. delivers high performance out of the box. It's easy to secure because tables are first-class resources within S3, and it does automatic storage cost optimization on your behalf based on policies that you set. That's our story on the structured data side of the house. Now, in terms of unstructured data, S3 has more than 400 trillion objects in the service today. It's bonkers. A ton of that is unstructured data, files. Images and video have become more and more prevalent in our lives. Customers continue to go through digital transformation, bringing more and more documents that were in physical copies online, and this has resulted in huge unstructured data stores that customers are sort of struggling to manage. Many customers have stood up metadata systems in order to keep track of all of the individual files that they have, which presents its own set of problems. When we talk to customers about large, unstructured data stores, what they tell us is that it's becoming harder and harder to find the objects that they need in order to execute on a task. We have many customers who have built metadata stores next to their unstructured data stores, but these are difficult to build, and they result in a dependency taken outside of storage, which complicates your resilience posture as well as security. And we've also found that metadata is only as valuable as it is current. And so if you're in the business of keeping and tracking metadata for your unstructured data stores, you're just on this constant operational treadmill to keep that system running as quickly as you can in order to keep metadata current so that it's useful. It was really this set of problems that led us to announce a preview of a new feature that we call Amazon S3 Metadata. Metadata does automatic metadata generation accessible via simple SQL semantics within minutes. Here's how it works. As your clients update a data set in a general purpose bucket, we add a row to a system-managed iceberg table within one of these table buckets that I just mentioned for every object mutation that occurs in the data set. So every put, every delete, every update to metadata. Each one of these mutations adds a row into an iceberg table. We call that table a journal table because it's really a journal of all changes made to your data set. The journal table is an AWS managed table. It's read-only for non-AWS principals. And the way to think about it in database speak is that it's really a system table for your S3 bucket. Okay? Now, it delivers 21 metadata fields automatically for every object added to your bucket. It tells you things like object size, storage class, some information about clients, some information about encryption, and on and on and on, up to 21 metadata fields that you can easily query using simple SQL semantics. Now, this capability of quickly getting access to S3 metadata via SQL commands within minutes of object creation, we think this is a powerful primitive, and we think that customers are going to come up with some really cool use cases for it. But I wanted to take you through the three use cases that we're most commonly talking to customers about leading up to the launch this morning. The first is around finding objects to process. Whether you're going to train against a data set, whether you're going to create chargeback reports to give back to one of your end users, or many other use cases, there's very often this part of the business logic in an application that needs to go out and find a given set of objects to go process. Being able to do this with simple SQL commands to filter and find the right objects to go get is just a very powerful capability, and we think it's going to simplify a whole bunch of applications using SQL instead of processing list requests or putting inventory reports through ETL pipelines, these sorts of like additional processing that customers are doing today just to find the right objects to go process. The second use case that we have in mind is that we think this capability will help customers to understand and track data lineage. Now, we know that data lineage is a mighty deep subject. And it's not our claim that this is an off-the-shelf sort of all-in-one data lineage capability or product. But we think that being able to query against metadata throughout time, it will be a very interesting building block for data lineage solutions. S3 metadata gives you the ability to determine a snapshot in time in the past, to determine a snapshot in time today, and to analyze the mutations that occurred between those two snapshots in time to better understand why your data set is the way it is now, right? And so these capabilities of being able to sort of understand in a more effective way how your data has evolved over time using SQL statements instead of processing logs or some other heavyweight processing technique, we think will be very powerful for helping with data lineage. And then the last use case we have for S3 metadata that we're most commonly talking to customers about is just helping you to learn more about your storage usage. And we have entire products for this. We have S3 Storage Lens, which does a great job like showing charts and graphs and helping to understand sort of trends and forces across your S3 estate. But there's really no replacement for being able to fire up a SQL prompt, to write a specific query, to answer a very specific question about how your storage is being used. And we think customers will do that with this capability. So those are the use cases that we have in mind for system metadata in this new capability within S3. Now, often when we talk to customers about this, one of the first responses that we get is like, that's fine. It's very useful to be able to use SQL to query metadata within S3, but I have my own metadata as well. And I want to enrich your stuff with stuff that matters to my business. And there are 3 ways that you can bring your own custom metadata to bear to enrich what we have with the system metadata that we deliver automatically. You can use S3's object tags to annotate your objects with custom fields, with custom metadata. Object tags will flow through to the S3 metadata journal table, and making them queryable for the first time since tags were launched in 2017. You can add user-defined metadata on your put request. This is a header in put. This will add immutable metadata to your object. Again, will be queryable out of your journal table. Or you can create your own custom table within a table bucket and join that in with a system table that we generate and maintain for you. The first biggest customer that we have for the user-defined custom metadata in particular is actually us. This morning, we also announced new video generation capabilities via Bedrock. Amazon Bedrock now automatically annotates any generated video that it creates as it drops it into an S3 bucket. You can see the example here of the headers added that translates into metadata annotated to these AI-generated videos that land in a bucket. And then you can see at the bottom an example query of how I might go query against my journal table to identify all AI-generated video within a bucket. This is just an example of applications integrating with this capability to give you interesting insight about how data is being created and by who within an S3 bucket. So that is the quick overview on the 2 big launches that were in Matt's keynote this morning. We have S3 tables for structured data, fully managed Apache Iceberg tables in S3. And then we have our new S3 metadata capability, which is in preview, that creates this journal table. It gives you the ability to go query S3 metadata with simple SQL commands. Next, we're going to take you through the fundamentals, starting with scale. Over the years, customers have created many, many S3 buckets. And there are some use cases that want to create actually a ton of S3 buckets. Specifically, applications that want to drive sort of a multi-tenant setup. Many of our ISV customers who want to service many of their own S3 customers, themselves bump up against our S3 bucket limit, which traditionally has been, actually for many years, 1,000 buckets per account. When you're limited by bucket counts, there are things that you can do in order to work around this. You can carve up a bucket to contain, so that it's usable by many applications, writing policies and storage management policies for individual prefixes. If that's not enough, you can spread buckets out across multiple AWS accounts. These techniques are absolutely correct. They're techniques that we totally support in every way. And while they're correct, we just don't think they're right. We don't think it's right for customers to add this amount of complexity to their applications because of a bucket limit. We don't think it's right, first of all, because we don't want you to worry about our limits. This is just another operational concern for you, and we wanted to take this off the table. Additionally, writing policies for a bunch of individual prefixes within a bucket adds complexity to the policy writing, and managing cross-account permissions. While we fully believe in a multi-account setup, it does add complexity, and we think a multi-account setup for the purpose of working around our bucket limits is bad. And so a few weeks ago, we launched higher S3 bucket limits. You can now create up to 1 million buckets within a single AWS account. That's a huge number, and when we announced that, we got a lot of snark about who would ever need 1 million buckets, and that's fair. I would just say our goal with this number was to get it off the table, get the limits off of the table, because we don't want you to have to think about it. In addition to the limit raise, we also added we actually launched a couple of changes to various other parts of the portfolio to help you manage a world where you may have thousands or tens of thousands or even 1 million buckets. We added support for service quotas for general purpose buckets. So now instead of calling support, you can go to service quotas in the AWS management console. You can see how many buckets you have. If you want to go past 10,000, which is the default limit now, everyone has a limit of 10,000, a soft limit of 10,000 buckets in all of your AWS accounts today. You can request that raise up to 1 million through service quotas. We also made changes to the S3 list buckets API, adding pagination and filtering in order to help you filter down and get shorter lists of buckets if you have tens of thousands of them. So that's what we did on scale. We're very happy to get that limit out of the way of customers, and we're looking for other limits to get out of your way as well. We believe that S3 should feel limitless to you, and it's always our goal to deliver that. Now, on durability, there are really 4 systems within S3 that deliver on our 11.9's durability design. We did, at the S3 deep dive last year at reInvent, we had some PEs that really drilled into these 4 systems in a lot of detail. That's linked here if you're interested in sort of the math and techniques behind the 11.9's of durability. I encourage you to go just watch that video from last year. Real quick though, the 4 systems in play to deliver 11.9's of durability are end-to-end integrity checking for requests to make sure that no bits are ever flipped as data moves through the system. We always store data redundantly across multiple storage devices. We always periodically audit data as it is at rest to make sure that data stays correct over time. And we spread data across multiple availability zones within a region. Those are really the 4 techniques, the 4 primary techniques that we're using to get to 11.9's of durability. The update that we made on Sunday was to this first one, to our end-to-end integrity checking. Just a quick primer on how integrity checking works today. When your client gives us an object, we take a checksum of that object at the S3 API. We take a checksum of that object after it's durably stored, and we compare those checksums to validate that they match. And only then do we return a 200 success response back to your application. This is a technique that we refer to as checksum bracketing. It's a durability best practice, and it's a very important technique that we always use when we're moving data around within S3. It's just a huge durability win to just make sure you're never flipping bits as data is being passed around between microservices. This allows you to know, bracketing allows you to know that that side of the equation is good. You know that you stored the bits that you got at the S3 API. What it doesn't allow you to know is that no bit was flipped as data was transmitted from your client to S3. This is especially true when that data is traversing the public internet, where it's bouncing across multiple network devices that are not owned by you or by us, right? And so to help with this, we introduced new data integrity defaults, improving data validation over the wire, and adding new checksum information into object metadata. So now with the latest version of the SDK, we take a checksum at the client, match that to a checksum that we take at the S3 API, and match that to the checksum that we take after data is durably stored. This allows us to prove end-to-end integrity checking over the wire from your application all the way down to storage, and allows us to protect that leg of the journey that is before data reaches the S3 API. Additionally, we store a whole object CRC checksum in object metadata. This is actually rolling out over the course of the next few weeks because it is a change to the default behavior of S3. And so every single new put, you'll start to see this CRC checksum within S3 metadata. You can see it in a head request. This allows you to go back and check our work. You can run this CRC on the client side within an EC2 instance from your laptop and compare it to what we say we stored. This is true even for multi-part uploads. It provides a whole object checksum that's verifiable by you at any time. So this allows you, at the end of the day, to prove durability over the wire across from client all the way down to storage. This durability posture, though, does become a little bit more complicated when we're talking about distributed applications, okay? With distributed applications, you have multiple clients that may write to the same key within S3. And so, for example, if we have client 1 here on the screen starting a multi-part upload and then happily starts to upload parts over time to a key in S3's key space, and client 2 comes around with a simple put object to that same key name, client 2 will get a 200 success response. It can successfully put to S3. Then when client 1 finishes the upload, it also gets a successful 200 response. And this right here is the sort of stuff that nightmare bugs are made of, right? You have 200 successes all around, and yet the payload uploaded by client 2 in this case was effectively never stored to S3, or was overwritten, even though it got a 200 success response. And so for these distributed application situations, in 2 launches, one in the summer and one last week, we introduced conditional requests for Amazon S3. You now have access to put if absent and put if match conditions to simplify durability for your distributed applications. You have access to what this means, if we go back to our little chart here, is that if client 1 is doing its thing and client 2 comes in and gets that success, completing the multi-part upload with a if no match condition means that client 1 will fail with a precondition failed error. This tells you that there's trouble in paradise, right? That you have a conflict between 2 clients writing to S3, and it points you in the right direction to go troubleshoot and fix that problem. You have access now to 4 new conditional request primitives. You can write if none match puts, right? So only successfully put an object if no key exists with the name that you're trying to assign. You can assign if match conditions. This is when you're intentionally overriding an object and you want to do a compare and swap operation. An if match condition allows you to do that. We have if match conditions for delete as well. These are available on directory buckets today, but will be available across the board very soon. If match conditions for delete allows you to be sure that you're deleting the right stuff, which is nice. And then we also have IAM condition keys So if you want to write a policy on your bucket that says only allow conditional writes, you have the ability to do that. So that's conditional writes. Those are the two updates to our durability over the course of the last several weeks and months. The last thing that I'm going to talk about before I hand it over to Mallory is a few updates that we made to security, starting with every AWS developer's favorite topic. Troubleshooting 403 access denied errors traditionally has been hard with S3. And the reason that it's hard is because there are so many places to hang policy that could result in a 403 error. You can write a policy against a bucket, write a policy against an access point, against a VPC endpoint. You can assign a block public access setting. You can set an SCP at the org level. There are just a lot of places where policy fragments get evaluated when we go to decide whether or not to allow a request through. And so when you get an unexpected 403 response and you have to go troubleshoot that, it can be a pain, which is why we added additional context to 403 errors back in August. We give more information for requests made within an AWS account to help developers to go figure out why they're getting the 403s that they're getting. This additional context includes the type of policy, the reason for denial, and some information about the principal who received the 403. Here you see just a few examples up on the screen, an example of a denial, an explicit deny based on a bucket policy or resource policy. You can see for block public access, we tell you that the 403 is because of block public access. Same with the SCP, right? If a request is denied because of an SCP at the org level, we let you know. This link is actually to the S3 documentation. There's a big update to our documentation on troubleshooting 403s. It includes more examples of additional context that we added as a part of this launch. I mean, the documentation update itself could almost be a launch, but if this is something that you find yourself spending time on, I would check out that doc. Amazon S3 access grants were launched last year at reInvent. They allow you to connect the permissions to S3 back to an identity provider within your environment, such as Okta or Entra ID or one of these directories. It makes it much easier to vend and revoke permissions to datasets in S3 as end users come and go from the business. Since last year, we've been busy with access grants, adding support for a bunch of services within AWS. Added support for SageMaker, Redshift, Glue ETL, Boto 3, as well as the V1 Java SDK. So we've been busy just expanding the universe of support for access grants, and we're very excited that customers are starting to adopt this and simplify their security at scale. One of the biggest customers that we have with access grants right now, and it ties to another launch that we have here at reInvent, is us. Mallory will take you through the transfer family launch that takes advantage of access grants later in the presentation. But as we were building that new capability in transfer family, we discovered that we really needed a new API in access grants, which is a list caller access grants API. This API allows you in code to determine for a given end user what data sets they have access to within S3. So if you have an application that wants to display and allow customers to browse and pick through the data sets they have permission to, this new API is an excellent choice to go do that. So that is what I have on the security side. And so now I'm going to hand it over to my friend Mallory.
Thanks, Paul. When it comes to performance, we know customers have more compute-intensive workloads than ever. Applications require higher and higher levels of transactions and are sensitive to tail latencies driving up compute costs. At peak traffic, S3 scales to receive 150 million requests per second, So today, I'll cover how we're optimizing up and down the request path, adding new features, both server and client side, adding new integrations, and launching in more locations than ever to deliver the performance that you need. Last year at re:Invent, we launched Amazon S3 Express OneZone, a new storage class that's purpose-built to deliver consistent single-digit millisecond first byte latency for your most frequently accessed data sets. S3 Express is able to accelerate data access reads by 10 times and reduce your request costs by 50% compared to standard. We're able to deliver that type of performance because we introduced 2 new design concepts into S3. Let me briefly recap those. The first is we introduced a new bucket type called a directory bucket, where for the first time you create a bucket and specify a single AWS availability zone to create your bucket in order to co-locate your objects to your compute workloads and reduce network-based latency. This type of bucket also comes with an upfront request scaling model built into it. The second is we introduce a new authentication-based mechanism that's based on a session token instead of on a per-request basis in order to reduce authentication-based latency. Our Create Session API is automatically built into the SDK and CLI for you. You combine these together, and S3 Express enables latency-sensitive applications to easily scale to millions of transactions per minute, all with high availability and high durability. It's great for use cases like machine learning training, interactive analytics, and media content creation. But we know that customers often rely on a large amount of other AWS services in order to unlock the value from their data stored in S3. So we've worked backwards from customer demand and added integrations with S3 Express. For your machine learning use cases, we added support with Amazon SageMaker to accelerate training jobs. Using fast file mode, we're observing up to a 5.8x improvement compared to S3 standard. We also added support with the S3 connector for PyTorch. And for your analytics use cases, we expanded support with Amazon EMR to include other deployment models, including Amazon EMR on EKS for your container-based workloads, and Amazon EMR serverless. For server-side encryption, we added support with Amazon Key Management Service with customer-managed keys. And for governance and compliance use cases, we expanded support with CloudTrail to include all data plane operations. We also added support for the S3 Lifecycle Expiration API to automatically expire objects based on age to help you optimize your storage costs. Another area of performance needs is in with continuous data workloads, so applications like logging, interactive analytics, and media broadcasting. Customers in this area have a constant amount of new data coming in, and they want to add data to an existing object. For example, let's say you have a logging application and you have a 100 kilobyte file, and you want to add just 2 kilobytes of data onto that existing object. Today, you can't do that all in one place since S3 objects are immutable. To deliver performance in this area, earlier we added support to append data with Amazon S3 Express into an existing object. So this simplifies applications that previously combined data in local storage before ultimately copying the final object back to S3. So let's go back to that previous example, and let's take that 100 kilobyte file, and now you'll use the S3 API and a new header to specify the portion that you're appending to the existing object. Once you get your 200 back, you can immediately read back the entire new object. And what's great is there's no minimum amount of the object to specify for the append. You also don't need any new permissions since it's a header in the existing S3 put API. You just need permissions to write. Lastly, you can repeat this process up to 10,000 times on a single object. So let's talk about where you can use this new feature. When S3 Express launched last year, we launched in 4 regions. And recently, we added support for 3 new regions, including Ireland, Ohio, and Mumbai. Speaking of geographic use cases, we know that some customers particularly those in public sector or other highly regulated industries, have data sovereignty requirements. These customers are required to store applications in physically isolated infrastructure and to store data in a particular sovereign location, many times without an AWS region in that location. So earlier this week, we announced S3 storage classes for AWS dedicated local zones. A dedicated local zone is a type of AWS infrastructure fully managed by AWS, built for the exclusive use of a single customer or community, and placed in a customer-specified location or on-premise data center. In dedicated local zones, customers can now create a directory bucket and specify a single dedicated local zone to store their objects in. As a zonal solution, S3 supports our 2 zonal storage classes in dedicated local zones, including S3 Express 1 zone and 1 zone in frequent access. In dedicated local zones, these storage classes are purpose-built to store data in a specific data perimeter to help you comply with your data isolation and data residency requirements. So here, your object data stays local to the customer-specified location where you've deployed your dedicated local zone, and your management data, like your IAM policies, your CloudTrail logs, and CloudWatch metrics, are stored back in the parent region. With support for storage classes in AWS dedicated local zones, this extends the AWS Digital Sovereignty Pledge and our commitment to offering the most advanced set of sovereign controls in the cloud. Up to now, we've been talking about all of our server-side improvements. However, at AWS, we think the S3 experience actually extends beyond our S3 APIs to include client software, SDKs, and connectors. So we believe it's our job to make them simple, easy, performant, and also act as a translating interface for applications that don't speak S3 directly. We tend to think of this as the on-ramp to S3. And so to deliver on those goals, last year, we introduced the client family for Amazon S3, including MountPoint for Amazon S3 and the S3 connector for PyTorch. So let's review both of those. MountPoint for Amazon S3 is an open source file client where you can mount a bucket on a compute instance and access it like a local file system. It automatically translates local file system API calls into S3 REST API calls on S3 objects. It's designed for high throughput performance and is based on the AWS Common Runtime Library for performance best practices. MountPoint supports the features we spoke of earlier today, including appending data in S3 Express and directory buckets in AWS dedicated local zones. So let's see how we'll mount those. When you mount your bucket, you can now use an incremental upload flag, and after that, MountPoint will automatically use the new header in the S3 put API for you. No other action is required. Also, when you're mounting a directory bucket or a general purpose bucket, mounting a bucket is the same. You provide the full bucket name. Specifically, though, for directory buckets, it contains the zone ID, which is either the availability zone or the dedicated local zone ID that you've placed your objects in. We've also expanded support for MountPoint's cache options, including a new high-performance shared read cache with S3 Express 1 zone. This cache can be shared by multiple compute instances and elastically scales to any dataset size. So let's take a look. First, when mounting, you'll now reference your source bucket, and you'll use the new cache type feature for this shared cache and reference a directory bucket to store your cache in. For best performance, we recommend creating a directory bucket in the same availability zone as your workload. Now, during initial read requests, MountPoint will populate your data into your directory bucket cache for you. For subsequent read requests on the same amount of data, this shared cache can accelerate reads by up to 7 times compared to S3 standard. If the object is unavailable, it'll route the request back to the source mounted bucket. With this cache, you're no longer bound by the provision size of your local instance storage, and you can scale with your directory bucket and S3 Express 1 zone. Last year, we also introduced the S3 connector for PyTorch to deliver high throughput for PyTorch training jobs that store data in S3. Since then, we've added support for 2 additional ML frameworks, including PyTorch Lightning, which automatically optimizes S3 read and list requests to improve checkpoint performance by saving data directly in S3 without saving to local instance storage first. And second, we added support for distributed checkpointing, a PyTorch feature for loading and processing in parallel. Distributing jobs can often run for hours, if not days. So here, the connector is able to optimize the network bandwidth between EC2 and S3 in order to deliver higher throughput. This can result in up to 40% faster performance compared to writing to local storage. Another client-side experience that customers asked us to help take a look at was to connect their end users to their data within their own applications. Today, to do this, customers typically write and manage their own custom UI or rely on a third-party integration that often provides little control, adds costs, or can be difficult to maintain. So we built Storage Browser for Amazon S3. Storage Browser provides your end users within your application a simple interface for working with data stored in S3. It's made available as an AWS amplified JavaScript and React library, and automatically optimizes for high throughput data transfer to S3 by using S3 multi-part uploads by default. Storage Browser only displays data that your end users are authorized to do so, and has support for 3 different authorization modes. First, you can use AWS IAM Identity Center with S3 access grants that Paul spoke about earlier. So this helps you manage data access at scale by automatically granting S3 access based on corporate identity. Second, you can also use Amplify Auth with Amazon Cognito, an identity platform for web and mobile applications. It's a great choice when you want to connect your third-party providers to data in S3 that aren't a part of your corporate directory. Or you can also bring your own managed auth service by vending an AWS STS token to Storage Browser. You can fully customize Storage Browser to match your existing application's brand identity, style, including buttons, headings, icons, and much more. So Storage Browser gives you full control to configure the component directly in your own application. But let's say you wanted something a little more managed. Here, we launched the AWS Transfer family of web apps, which is a user-friendly browser-based experience that is powered by Storage Browser for S3. With web apps, you get to provide your workforce with a fully branded, secure, web-based portal for end users to browse, upload, and download their objects in S3. This enables a browser-based transfer with a user-friendly interface and URL. You can create this shareable URL in a few clicks from the console in the AWS Transfer Family console. Then your authenticated end users can access the data that they're authorized to do so using S3 access grants. So this offers the same setup and benefits as Storage Browser without the need to manage application infrastructure. Within web apps, you can also customize the logo and title to reflect your branding. Another similar problem is static website hosting. Customers today can use S3 buckets to store their content, but outside of S3 have many more tasks to still do, including managing their DNS, setting up logging and monitoring, and many more common tasks. So to help innovate in this area, we've added a new integration with Amplify Hosting. With just a few clicks in the S3 console, you can now connect your S3 bucket to your managed website with AWS Amplify Hosting. It remembers the connection between your bucket and your deployed app so that you can update your content within a single click. You can get started and create this connection to your Amplify app from the Properties tab of your S3 bucket. and that has been 30 launches in 60 minutes. We covered our new features for structured and unstructured data with S3 tables and S3 metadata tables. We expanded on our storage fundamentals with higher bucket limits, new conditional APIs, and new checksums. We spoke about how we're delivering performance with integrations with S3 Express One Zone and expanding to AWS dedicated local zones. We talked about client-side innovation with MountPoint and PyTorch, and storage browser and transfer family web apps. I want to thank you for joining us today. We're looking forward to your feedback on these features and what you'll build next.